Hello and welcome back to the optimization method course. We are going to talk about a new topic and it's about game theory. I'm going to start this topic by talking about saddle points. So let's start. In the operations research course in general, we mainly discuss the situations in which we only have a single decision maker, and that decision maker needs to choose an optimal decision, right? Like in linear programming, nonlinear programming, you would like to minimize or maximize something with a set of constraints. However, in reality, especially in many business situations, usually there are two or more decision makers. They are all simultaneously choosing an action. And the action of one person affects the other, of course, right? So game theory is a useful tool for cases where we have two or more decisions makers, and usually they have conflicting interests. So now we are going to solve a problem where we have more than two decision makers and they have conflicting interests, and we're going to see what would be the optimal thing to do for each decision maker. Let us start with a situation or games that are called zero-sum and constant sum games. These games involve two persons. In these games, what we're going to do now is trying to identify whether that game has a saddle point or not. Here are the characteristics of a two-person zero-sum game. The game involves two players. One player is called the row player and the other player is called the column player. You can see here that row player may choose one of M strategies. So there are M rows because row player may choose one of those M strategies. On the other hand, column player may choose one out of N strategies. Therefore, we have N number of columns. And then this matrix is called a reward matrix because the value inside the matrix, Aij, it means that it is the reward for the row player to play strategy I and column player playing the strategy J. So A21, for example, means that the reward that the row player will receive if he or she is playing the second strategy, and at the same time, the column player is playing the first strategy. So the reward in the reward matrix is always denoting the reward for the row player. Okay, so for the column player, you may interpret this value as follows. So A21 means that the column player loses as much as A21. Okay, so A21 is the reward that the row player receives, but you can also think of A21 as the loss that the column player experiences. So that's why it is called the zero sum game, because the sum is zero. Um, this is the amount of the row player receives, and this is also the amount that the column player loses. So one receives something and the other loses something with the exact same amount. That's why the game is called zero sum game. Let's see an example here. Suppose we have a reward matrix that looks like this. It means that the role player has two strategies that he or she can choose, while on the other hand, the column player has four possible strategies. So the matrix is a 2 by 4 matrix. And this value here, 2 on the circle, it means that if the row player plays the first strategy, and the column player plays the second strategy, it means that the row player will receive a reward of 2 units. for example, like $2. And at the same time, at the same conditions, the column player will lose $2. So the sum is 0 because the row player receives $2 and the column player loses $2. In game theory, each player chooses a strategy that enables him to do the best he can, assuming that his opponent knows the strategy that he is following. So we assume that our opponent knows which strategy that we are going to play, and then under that condition, we try to do our best. Let's try looking at this assumption using a matrix of 3 by 3, which means that the row player has 3 strategies, and then the column player also has 3 strategies. Okay, now assuming that we are now in the position of the row player, and then assuming that column player, our opponent, knows the strategy that we are going to play. So our opponent knows that we are going to play the first strategy. So the column player obviously will pick the strategy that minimizes the reward for row player. In this case, the column player will play the first or the second strategy, because the column player again is assumed to know that we, the row player, is going to play the first strategy. So the minimum is 4. Again, if the column player knows that the row player is going to play the second strategy, the column player obviously will pick the third strategy, because the third strategy for the column player minimizes the reward for row player. So the minimum for row 2 is 1. 1 here is the minimum reward that a row player will achieve if he or she is playing the second strategy. Now, if the row player plays the third strategy, and then again we assume that the opponent knows that the row player is playing the third strategy, the opponent or the column player will pick the second strategy. Again, why? Because the second strategy minimizes the reward that the row player will receive when the row player is playing the third strategy. So this is the minimum if the row player is playing the third strategy. Assuming the column player knows these 3 possible strategies that the row player is going to play, the row player can, the optimal strategy for the row player is to pick the third strategy, which means among all strategies, and then in all of these strategies, the column player try to minimize the reward for the row player. The best that the row player can do is picking up the third strategy. Why? Because if the row player picks the third strategy, whatever the column player tries to do, the most that column player can do is to minimize the reward for the row player as much as 5. Suppose the row players trying other strategies, you can see that the column player can do much much worse to the reward of the row player, right? If the row player picks the first strategy, column player can make sure that the row player only receives $4. If the row player selects the second strategy, then column player can make sure that if the column player plays the third strategy, then the reward that row player can receive is only $1. So the best that row player can do is to pick the third strategy. Now let's talk about the side of the column player. If we are the column player, and the role player, our opponent, knows the strategy that we are going to play. In this case, the first strategy. Then the role player will pick the one that maximizes the reward for role player, right? Because remember, these values are always the reward for role player. So if the role player knows that the column player is going to play the first strategy, the role player will pick the third because it maximizes his or her reward. If the role player knows that the column player is going to play the second strategy, the role player again may pick the third strategy because it maximizes the reward for role player. And then if the role player knows that the column player will play the third strategy, the role player will pick the first strategy because it maximizes the reward for the role player. So here the maximum for each of the column strategy is 6, 5, 10. And remember, these are the rewards for the role player. So the best that the column player can do is finding the strategy that minimizes the reward for the role player, which is the second strategy, right? Because let's say if column player picks the first strategy, the role player may play the third strategy such that the role player receives $6. If the column player picks the third strategy, the role player may play the first strategy such that the role player receives $10. If we are the column player, we do not want the role player to receive a lot of money. So the best that we can do here is to pick the second strategy such that it will minimize the possible reward that the role player may receive. Now you see that we have a saddle point because the best that the role can do is receiving $5, and then the best the column can do is to let the role player receives $5 as well. The formula is that if you take the maximum of the row minimum, and then if you take the minimum of the column maximum, if the value is the same of these two, it means this game has a saddle point. If saddle point exists, then the corresponding value is called the value of the game. So the value of this game is $5. Or in other words, the value of this game is that the role player will receive $5. And that is the equilibrium point. It is called the saddle point or equilibrium point because neither player has the incentive to move away from this strategy. So the saddle point says that the role player should play the third strategy and the column player should play the second strategy. And anybody who moves away from these strategies, he or she will lose something, which is the role player will gain less than $5, or the column player will let the role player receives more reward than $5, which is not desirable from the point of view of the column player. So now let's see what happens if, let's say, role player is moving away from the optimal strategy. We know that the optimal strategy is playing the third strategy, while on the other hand, our opponent sticks to the same strategy. So we know that the column player will stick to column 2. Let's see what happens if the role player is moving to the second strategy. So if the role player is playing second strategy, while the column player sticks to the optimal solution playing the second strategy, the reward that the role player will receive decreases from $5 to 3. So it's a loss for the role player. Similarly, if the role player moves to the first strategy, while at the same time the column player sticks to the optimal strategy, again, role player experiences a loss. It only receives $4, while if he or she sticks to the optimal solution, the role player will receive $5. So you can see that the role player has no benefit of moving away from the optimal strategy. Similarly, if column player tries to move away from the optimal strategy of the second strategy to either the first or the third, he or she will experience a loss, supposing that the role player stays in the optimal strategy. So if the column player moves to the first strategy, then the role player will receive $6. Or in other words, the column player will lose $6 instead of just 5. Again, if the column moves to the third strategy, while the role player sticks to the optimal strategy of the third strategy, now the role player will receive $7. Or in other words, the column player now is losing $7 compared to just 5 if the column player sticks to the optimal strategy. So again, we see that the column player should not move away from the optimal strategy. So if a game has a saddle point, like what we just saw in the previous slide, we may find the optimal solution for each player. And then anytime those players must stick to their optimal strategies. Nobody should move away from that optimal strategies because they will experience loss if they move away from their optimal strategy. Now, there are games that do not have saddle points. For example, this reward matrix, if we try to find the maximum of the row minimum and then minimum of the column maximum, we will see that those values are not the same. In other words, this kind of game does not have a saddle point. If the game does not have a saddle point, then the optimal strategy and the value of the game is different with what we've done for the game that has a saddle point. We are going to discuss this kind of game later. So that's the end of this video. In the next one, I'm going to talk about constant sum game. So see you on the next one. Thank you.